right, so class number 2 today, we're going to talk about sensors and signals, primarily temperature sensors. We've got some sensors here that we'll play with in a little bit. We want to cover thermistors, RTDs, because those are the two primary types of sensors we use on campus. We want to also talk about some of the signals we see. And we have various devices that are out there that aren't just temperature sensors, but they could be pressure, flow, things like that. They also use, they transmit via the signals of either 0 to 10, 2 to 10, 0 to 5, 4 to 20 milliamp. And so we're going to talk a little bit about those signals and how they work. First off, how many of you know or have heard of a thermistor? Okay. Anybody know what a thermistor does? Tell us anything about it.
Temperature.
It reads temperature. Okay.
Resistance.
So, does it read the temperature, or what does it really do?
The resistance, the temperature changes, the resistance changes.
Okay. So as I experience a rise in the temperature or a decline in the temperature, the resistance of that sensor changes, right? It goes either up or down. Now, when a thermistor warms up, does the resistance go up or down typically?
Down.
Okay, so for a thermistor, the ones that we use primarily on campus are what they call an NTC, or negative temperature coefficient. So that means the temperature is going down, the resistance is going up. They're opposite directions. The temperature goes up, the resistance goes down. Okay. They do have positive coefficient thermistors, but we don't use those on campus. I'm guessing primarily they're probably cheaper to make on the negative. Otherwise, we would be doing positive, right?
There's no difference.
Yeah, because it wouldn't matter. They may be more accurate based on the materials used to create each as well. So I'm not entirely sure why we use the negative, other than it's either got to be a dollar or an accuracy thing. So there's RTDs. We're going to talk about RTDs a little bit. And RTDs are a direct response. So as the temperature goes up, the resistance goes up. And so I'm going to show you a graph here in a little bit that kind of compares the two and shows you how they kind of respond. Why do we use thermistors primarily on campus? Okay, we talked the Johnson stuff. They use
Is that because we're
RTDs.
backwards?
Because we're backwards. Yes. No. Not because we're backwards. Why do you think? Because we do have some RTDs. Our BTU metering, we use RTDs. Johnson Controls uses some RTDs. But the majority are wall sensors, the discharge sensors and air handlers, mixed air sensors. Those are going to be thermistors. And why would you guess we use those?
Chilled water pumps at the new plant have RTDs on the
There's
bearings and the
yeah.
windings.
Probably cost.
Okay. Cost is the big driver. It really is. The cost per accuracy is a much higher thing with RTDs than with thermistors. And so, do we really need to know if this room is 75.321? No, we don't, right? If it's 75, that's probably, within a degree, we're probably okay. That's what we deal with at home, right?
That's why you need those offsets sometimes.
Yeah. So we don't need the accuracy, and so what we do is we use the thermistors because they're a much cheaper sensor. I mean, these sensors that we'll kind of play with here in a minute, these are probably $1, if not even less, to produce or to buy. They're very inexpensive. Okay, so they don't cost a lot. Whereas a platinum RTD, there's going to be some cost. We're going to talk about not only do you need the sensor, but there's some transmitters and other things that are involved to make them work. So the primary driver is the cost. Now, on campus, we have four main systems that we will deal with. We have Johnson, Stapha Smart 2, Stapha Talon, and Delta. The Johnson controllers use platinum RTDs. They're 1,000 ohm platinum RTDs, and we're going to talk about those in a minute. The Stapha Smart 2 uses a T30 thermistor. Now, I don't know what the range is on a T30. I don't have that chart. But the T30 is like the wall sensor for this room here. That little temp sensor for this particular room, because it's a Smart 2 control, will have a T30 sensor in it. If we pull the cover on it, you'd see that little sensor just kind of hanging out in the air a little bit. Okay. If we're in a Stapha Talon area that's being controlled, that's going to be a 10,000 ohm thermistor. Stapha Talon uses a type 2. You guys will pass this out and just take one and get the rest back. We have different ranges on these different types of sensors. The Stapha Talon, like I said, is a type 2 10,000K thermistor. When we go to Delta, we use the same 10,000 ohm type of sensor, but it is a type 3. So that means that both of them, Delta and Stapha Talon, when it is 77 degrees, will be identical in temperature. They will be 20,000 ohms. Okay? But as we move away from 77 degrees, get either warmer or colder, the scaling is different. So one goes up and down quicker than the other one. Okay. So if we use a Delta thermostat on a Talon system, will it work? It'll work really well at 77 degrees. But as I start to move away, then I get inaccuracies that start to come in. Okay. And that could be several degrees by the time you're 30 degrees away. So we want to make sure the sensors are matched. So with a thermistor, it is a curve. It is not linear. And so that curve is over hundreds of degrees. And so if we have a gentle curve over that, as long as we pick a fairly narrow range, we can get a pretty linear equivalent. That makes sense? So as long as I'm not trying to go from minus 200 degrees to a positive 200 degrees, if I want to do 0 to 100, that's a much tighter band. I'm going to be a lot more linear for a thermistor in that range. RTDs are far more linear, and that's why we use those for the accuracy when we want to do BTU metering and other, like the North Chiller plant. They wanted everything exact, and so they used more of the RTDs, those higher precision kind of transmitters and stuff like that.
They're using them as a safety
Yeah.
to shut the pump off.
Yeah. So and on those motors especially, they don't want any chance that they're a few degrees off, because we're talking thousands and thousands of dollars if one of those goes out, plus the downtime of the system potentially. So let me show you that.
How much are the RTDs versus these little thermistors?
These are less than $1.
They're probably. I'm
That's what
guessing
it
a buck or two. The RTDs $20 a piece.
Oh, okay.
So I mean it's
Quite a bit.
quite a bit. Now, a lot of the sensors we get are encased in like a probe with a mounting. This thing here is just a raw sensor, and so this guy's going to be pretty cheap. I put a little metal jacket on it with a little plate to mount it, and then you're up $12. So, the sensor itself though is quite a bit cheaper for the thermistor as opposed to the RTD.
So the RTDs we use a lot because of our high temperature requirements, so the ambient temperature these probably wouldn't tolerate, I don't know.
Yeah, and that's another thing, is that certain sensors can work in certain temperature ranges, right? So there's certain RTDs that you're not going to run on high temp stuff because they haven't been built to withstand 400 degrees. That's too hot. It'll melt them the solder joints or whatever they've got in the sensor, it'll all come apart.
Yeah, and then the really high accuracy ones are matched RTDs
Yeah.
at the factory, and then those, I think we're talking hundreds of bucks.
Yeah, so you get paired ones, and they're put into a system together. So there's two of them in the same sensor. I believe is how they showed it. It's like four. Well, it's actually four. Was it four or just two?
We have, we have dual RTDs, and sometimes there'll be two.
Yeah, yeah. So there's some things you can, yeah. So you can, they're dual element, and they're funky to look at how they're wired, but they kind of work, and that way you're more accurate. So here's kind of a comparison between a 100 ohm RTD, so a platinum 100 ohm RTD, and what's saying there, a 2252 thermistor at 25. But you can see there's more of a curve to that thermistor as it comes down, and it's negative, right? As my temperature goes up, my resistance is coming down, whereas my RTD, a much flatter line, and it's getting higher and higher as we go higher with temperature. Okay. Now, why do we care? Why do we care about this graph here?
You gotta know what you're dealing with.
When you guys go out in the field and have to troubleshoot a sensor, you're going to have this in your pocket, right?
Yep.
Pull it out. You get your magnifying glass out. I should be right there. No, you're not going to do that. But to understand the properties of how these sensors work will help you as you troubleshoot problems. Now, the sensors we have here that we're going to play with in a little bit, those are 20,000 ohm at 77 degrees. So on the chart that you have here, it is the far right column. Those are the pre-con type 4s. We on campus, like I just said, we use the 10,000 ohms, which is the type model 24s and the model 3s. So type 2, type 3, those are going to be what we're going to run into a lot more often. Okay. Now, if what I'd like to do is have you look really quickly and find out what would the resistance be for an average discharge error on a fan system if you're 55 degrees for your average temp for a type 2 10,000 ohm thermistor.
17.44.
Okay, so we're 10K at 77. We've gone up to 17,000 when we hit 55 degrees. Now, why am I picking 55? Yeah, a lot of times we're around 55 degrees. So if I go and put a meter on something and I'm not remembering this chart because it's not in my hip pocket and I didn't memorize it, but I put my meter on it and I read 16,000 ohms, 17,000 ohms, 18,000 ohms, I'm like, that seems, it's kind of like the reality check. It's like sanity check or whatever. That seems in the ballpark, right? All right, now let's look at room temp. What would we be at 72 or 70? We'll say it's
11.8.
okay, so we're just a little bit above our 10,000 ohms, right? We're 11,000. Okay, so again, I put my meter on a space temp, and if I'm somewhere between 11 and 10,000 ohms, that sensor's probably reading pretty good. Okay, what about discharge air for a hot deck? Say I'm up at 90, 95. What's 90 degrees?
7,331.
All right, so 7. Now, so here's the reason I picked 55 and 90. 17,000, 7,000. Okay, those are a couple numbers, and then 77 degrees. We got a lot of 7s there, right? So 10K at 77. I should be 7K at 90, 17K at 55. Everybody follow that? Just one of those little things you can put in your, kind of in the back of your memory somewhere, and then just as you're measuring things, I'm not pulling out the internet to see what it is, but it just, hey, that seems like I'm in the ballpark, right? So hopefully that kind of helps as you troubleshoot. So let's talk about troubleshooting these a little bit. A lot of times we get something like this, right? If I can get it to the right level, there we go. Does this look familiar, Brett?
How come,
What?
how come it doesn't go have a decimal through that period, just because it's tighter range, or?
Where are you at? Oh, down below?
Yeah,
The 90 degrees.
Drop below
Less than 10,000.
Yeah, it's,
Oh, okay.
yeah, I think once you get to a point where they can show a decimal, you're not so,
Okay.
but really when we're talking a tenth of an ohm, I don't even know why they put it on here really. It doesn't, I mean, that's such a small change, it's really not gonna matter. So here's a couple sensors. This is over at the data center glycol off of the chillers up there. So some of you guys have worked with this and been in that area. We have 2 heat exchangers. The chillers upstairs run glycol from up above on the roof down to the heat exchangers using glycol. The heat exchanger then transfers or extract the heat from the cooling loop that goes to the data center and then cool that down through the heat exchanger, right? So here I have a couple sensors. I'm looking here, I've got a glycol supply temp, and it's not reading correctly on the graphic. So I go over there, I got my meter. How do I troubleshoot? And I'll zoom out just a little bit so that we can see a little more. How do I go about troubleshooting that particular sensor? It's this first one here. 15 and 16 coming into this input number 10. What would you do? You got a meter.
Disconnect with 15 and 16.
Okay, so most of you have all had an opportunity to do this. Because we don't know what this controller or anything here is doing to the circuit, we want to disconnect any interference or any outside influences. So I disconnect my wires at 15 and 16, and I put my meter on them, and do I turn to volts AC, volts DC, resistance, capacitance? What do I look at?
Resistance.
Okay, we're going for resistance, right?
On
Because
this, yeah.
we're not powered on the circuit right now. This is just a raw sensor, just happens to be at a very long length of wire, right? Maybe it's 300 or 400 feet out there. Okay, so I put my meter on there. If I was running 45 degrees, what should I read? And this tells me here,
21,
I'm a 10K NTC type 3, right?
21.
22, 76.
26.
So 45
26.1.
21.24.
At 40?
at 45.
Oh, so
45.
45 is 22.
21.24.
21, so are you on the type 3 or the type 2? Make sure you're on the right.
Type 3.
Okay,
Type 3.
21.
so we're 21 something, right?
21.24.
And you just get your temperature
24.
for the pipe off of your temperature that
Yeah.
your
Yeah,
thermometer.
so say there's a thermometer on it, or you maybe have one of those thermal guns that you can shoot it. So right there, you have verified that the sensor is working. True or false?
No false.
Well, if
Just that the
the
thermistor is working.
the thermistor is working, if you've got that temperature.
Okay. Now, what happens if you have one of the wires nicked and is shorted to ground? Will you still read that temperature or that resistance?
Can, yeah.
No, I don't think so.
To ground?
You got
Yeah,
more-
I
you
think
got more
you
resistance.
can.
Okay. So this wire, is it a shielded wire? It's non-shielded. So there's really no path. If I'm touching a conduit somewhere, this wire has no path to complete the circuit, to short circuit the resistance on the end, right? It's kind of like if I have two wires and I just have a little wire hanging off the side, that wire off the side doesn't do anything. But once I hook it back into this board, is the board grounded?
You did?
Yeah.
Ah,
Yeah, 'cause you were.
so I've got a ground tied to this, potentially. Not always. A lot of times we leave a floating ground, but we could potentially have it grounded. All of a sudden now, then I've got zero resistance and it comes right back through the ground. Okay. So Eric brought that up in the first class. Says, what if I'm nicked? How does that change it? And it was a good question because you can read the resistance if you just do the two. So what also should we do then as we're reading it? Yeah, try at least one of the legs to ground, because we know if you do at least one, you're going to see the resistance of the original. But I should see how much resistance. You should be open, right? It should be like infinite, or it should say OL kind of thing. And so if it doesn't say OL, if I'm reading 10K or 11K, or then we know that there's some. So I check the other lead, and then maybe I've got the ground on the other side, okay, on the other wire. Okay. All right. So say I've checked that and everything seemed to be good. Sensor doesn't go to ground anywhere. I'm reading my 21 something on the resistance for a 45-degree pipe. What do I do next? I'm still having trouble.
So it's reading their own.
So on the graphic, it's either not reading, or it's totally like it's zero, or it's not reading correctly.
Then you hook it back up and go down to your,
Yeah, check your
To your
wires
board.
from.
Okay, so we go to the next point that we could possibly have an issue, right? Wiring between terminals and controllers is never wrong, right?
never.
Never.
No.
It's always right.
Okay.
Where you got your nick.
Tell you all sorts of stories, right? Everyone's got their
But
horror.
see, we get it from Atkinson, so they're
Yeah.
perfect when they come
That's
in.
right. So, do any of you guys know Gary, who's been wiring panels up there for years? The older Gary. I don't know how he does it. He does a phenomenal job. Now, he doesn't do them all, and he's not perfect. But out of thousands of wires that he terminates and stuff, he does a pretty dang good job. But data center, that big monster panel down in the data center, there's a lot of wires in there. And when that first came down, it was not perfect. There was a lot of fixing we had to do. So it happens, right? So yeah, the next thing is we trace this out. So reading a schematic, how important is that in what we do? Okay, it's pretty important. If you feel that you are struggling at all with schematics, find some on a regular basis and go through it. And if you're not sure what something does, ask somebody. And the more you do that, the more you'll come to something like this, and you're like, oh, I know what that is. I remember the very first time when I was asked to build a panel in the air conditioning shop as a student. I saw one of these here, which is a relay contact. There's a relay sitting on the side. I'm like, I have no idea what to do with this or how to wire it up. Okay? We're all at that point, to the expert, somewhere in between at one point or another in our life. So don't be afraid to ask, because you're only going to make yourself better by doing that. So we follow this line, and in the panel, maybe we identify a color of wire, we trace it out and bring it back, disconnect from the controller, whatever you need to do. If we find that that wire has a problem, and it could be maybe this wire's on 7 instead of 8, could be that it's not terminated correctly. We use the terminal strips that we typically use nowadays are spring kind of loaded terminals, so that as you push down a terminating screwdriver, you kind of unload the spring, put the wire in, and then you pull the screwdriver out, and then that snaps back, and it actually jams the wire via a spring into a metal contact surface inside. They're very good. I've even cut the total end of the stripped part off, so it's just a butt, like a butted end, and put that in there, and that spring will push it into the metal and still make contact. I mean, I've tried to sabotage these little demo panels that we're going to work on in a few weeks, and it's tough. You almost can't make it not connect. And so the older style where it was a screw down, those aren't nearly as good. They can come loose over time. Somebody once told me that amusement parks, by code, have to use spring-loaded terminals. They can no longer use screw-down terminals, because if you lose a wire on a roller coaster and something doesn't work right, that's not a good day, right? So yeah, we want to check one end to the other. If I get to the point here and I pull this wire off, how do I measure? What should I be measuring if I pull that one wire off? How do I especially I got something like this where I've got a,
All of them hooked to one ground.
yeah, can I still measure and check it?
Yeah.
Okay, where do I put my meter?
On the ground.
Okay, so there's a couple different places. I could try it here, but again, we're trying to get back to the controller, right? So I'm going to find where there's a ground. Now there's a ground here, but there's no wire. Can I use that one? Usually you can, because internally the grounds are all tied together. Now, there are some controllers that doesn't work. If you're not sure, go ground to ground and see. And you should get, like if you do continuity, you should get the tone or whatever and it should work. But I can always come where my ground comes into this one. I can put my one side of my meter here, the other side of the meter to that wire, and I check it. Everything's good. What's my options then?
If everything's good from there, then you've got something internally inside of the board.
So the controller is probably where the problem is. Now, if I have an available input next to it, that's my next step, right? Try another input. Get, if I can't set up the controller to do that, get help from our controls group, or have them come show you how to do it. I mean, the more we learn, the quicker we can get through some of this troubleshooting, the better. So try another input. If that still doesn't work, could be the board, right?
But I've also ran into where somehow the programming got glitched inside of the board. So it's not physically the board's problem,
It's the
but
program.
It could be
It's showing
programming firmware in
showing
the
this
controller.
temperature, but the program
it's supposed to be
is not.
negative and got changed to positive or something.
Okay,
like
so
that.
before we go rip out the controller, we then ask our friendly neighborhood control guy, can you go trace this point in software that came through on that input, trace it back and verify that I'm really getting that point to the graphic. Maybe it was a different one that looked like it was the right one. Okay.
Ping it.
What's that?
Ping it.
Ping it, yeah. So there are a few things that we can do to try and check, and it depends on the controller type. Do you guys know what in Johnson you do to verify some of that? Can you guys go and kind of trace it back through the software and that? Okay. All right. We're using,
This remind me of like a flame sensor in the furnace,
yeah,
kind of similar.
okay. And we talked about there's a flame sensor that you actually use 4 to 20 milliamp. I may not have the right terminology because I'm not residential backed. Is that what it is? The flame sensor has a 4 to 20 milliamp signal?
It's a million.
A milliamp. Okay. And so with that, and we're going to talk about types of signals that we use, whether they're the resistive type, or whether they're a voltage or a milliamp. Here in just a second. So.
That's we had a few of those that we had that were the points they brought out were the wrong, so it wasn't changing even though the room was getting really cold. So instead it was warm, we just put the wrong point on there.
Yeah, and I've seen that where either like you've got that scenario, or in the configuring of this device, this is input 10, but somehow I put 9 instead, and 9's looking at something that shouldn't be, and so then you don't get things working right. So, yeah,
A lot of times you're talking about initial setup right now, but there's times after the initial setup that temperature in the room, like the outside temperature and the temperature in the room, has been constant, and you find that out later.
nothing's ever
Because
changed.
something's changed down the road, and then you're like, how did this not get? But
Yeah.
it's just
Once in a while it's like 3 years down the road, and you're like, how has this operated for 3 years and no one's ever caught this?
Another thing to look at, like up at the Harmon building, redid the controls on the air handlers, but from design, the drawings, things changed. So you look at them, kind of look over them, they got some red lines, a few inputs, outputs have changed, and get that back to Atkinson or
Yeah.
whoever's doing the controls, let them know we need to update these
It's
drawings
really
to match what
important.
actually happened out in the field.
Yeah, and I can guarantee you that the best intentions and best engineering that goes into a panel can be changed that quick just because wrong information was given up front, right? I have a different size pump or a different style of pump or a fan. I have extra sensors that I didn't know about, or ones that I thought were there that aren't. So there's always these little things that happen once you get out there. We used to call it crowbar engineering, right? You have to get actually out there, open it up, see what's really there to really get it right. And sometimes that doesn't happen till you're starting things up.
So just today we have a good unit Elford building in that. One of the four compressor was locked up and we tried to reset it.
Mm-hmm.
So we turned on the power. It was working before. I mean the old compressors, the old three. We turned them off and after that we put it back on and didn't do anything. We spent like 3 hours there just trying to figure it out. And we check everything and they say air proving set switch. It wasn't working.
So
Compressor switch.
you had a safety that
But
it
it wasn't that because it was the outdoor machine was reading that, but the other one, it wasn't communicating with the indoor.
So you had a problem from the outdoor to the indoor,
Exactly.
and even though things were right,
Yeah.
that link
And
wasn't
so
made.
we turn on the power, we produce that problem.
Okay.
You know, and after that we just spent a lot of time and made sure the control board was okay and the programming was okay, and finally we just turned on the fan inside manually, and we set the unit outside, and after that it just went working fine. That's kind of,
So
it has something there, but
do you think things are good, or does it still need some work?
for what we know, there's another guy that had been had problems before, and he just reset it a couple times. We didn't know that. So you have to reset when the indoor, when the
So you have to
fan is
reset
running.
both of them?
Yeah, exactly.
Okay.
I don't know what's going on. That's how they
So we do run
communicate.
into some weird things like that where there's, maybe it's not the sensor exactly, but it's
Yeah, it
things that
wasn't
help
the sensor
transfer.
because, but that's what it was reading.
Yeah.
Yeah.
All right. Where did we go? All right. It's hard to run a computer when you're looking at it that way. All right. We've talked about thermistors, and I want to talk a little bit about RTDs, but I want to ask one more question. Here we're saying a thermistor instead of an RTD. Do we need to be super accurate for glycol or even chilled water? If we're a half a degree plus or minus a degree, we're probably fine, right? We're not doing energy billing off of this. We're not controlling the life safety thing. 45 is going to cool us just about as good as 44 and a half or 44. We're not quite, but it'll help. We use thermistors, and again, I got to remember if I've repeated myself in this class or this last class. Why do we use thermistors over RTDs?
Cheaper.
Cheaper.
Because when
So-
that gets broke off the wall right there, it's
Right.
gonna cost.
And so cost is the big driver. As we looked at that little curve, they're pretty accurate in the ranges we need. But one of the things is I have 10,000 ohms sitting out at the end of that wire. How much resistance is 400 or 500 feet of wire going to add to that overall resistance? Because if it's the wire plus the thermistor, that's my total resistance that the controller sees. So if I've got 18 gauge wire and I'm running, say, 500 feet out to the sensor, which is a pretty long run, 500 out, 500 back if you go, with the following the electrons, what's the kind of resistance we could expect on that length of wire? And I'll give you a range. Is it 2-3 ohms, 20-30 ohms, 200-300 ohms, or 2,000-3,000 ohms?
Only 2 or 3.
500.
500. 1,000 total, 500 out, 500 back. I mean, it's one wire, but you're two conductors in that one conduit or that cable.
So can that wire going far away during that period is touching different temperatures? Can that make a change in the resistance?
It could, yeah. I mean, if the wire is either hot or cold, that can
Yeah,
change things a little bit.
The areas that you go through.
Yeah. But if you're doing 500 feet, and you're probably a little bit more than that, it's probably more like 5 or 6 ohms is all you're going to see. So 5 or 6 ohms compared to 10,000, is that very much? It's pretty minimal, right? We're really, we're tenths or hundredths of a percent that it introduces error-wise. So if we don't care about a half a degree, is that wire length going to make any difference? No, it's insignificant. We've got more error in the sensor itself than in the wire introduces. Okay. When I start talking about RTDs, it's a little different. RTDs, we deal with either 100 ohms or 1,000 ohm RTD. So let me go back to this other this slide here. So notice here, I'm going from 400 degrees Celsius down to minus 200, and I'm, maybe 30, all the way up to 100. So that's not very far, right? That's not very many ohms that it's changed in the course of that range. So what's my 6 ohms of length of wire going to do to an RTD?
Inaccurate.
It's going to be a big piece, right? So, and I can't remember, I read it somewhere earlier, but it's somewhere like 3 degrees per ohm for a 100 ohm RTD. So if I got 6 ohms, you know, yeah, that could be a fairly big error. So we got to be careful with that. Now, there's a couple ways that we get around that, and that's what we're going to talk about when we get to our signal stuff. What other types of sensors do you guys run into? Well, we've talked about the 2 temperatures that we use. The RTDs are typically for the high precision. The thermistors are for our general use, cheaper kind of general range of temperatures. You know, 0 or minus, even 0 degrees Fahrenheit to 100 degrees Fahrenheit, kind of those range. What other sensors do you see out there?
Thermocouple for temperature.
Okay, thermocouple. How does the thermocouple work?
We have it's a bimetal, 2 metal wires, and wherever they're soldered together, that's the junction of the joint, and then when it's exposed to heat, it generates millivolt,
Okay.
and then
So heat causes an electric current to flow. It's essentially like a little temperature-based switch, right? It just has to do with milliamps instead of an on-off type thing.
and then depending on the metals that they use, it's classified as a type J, type K, or whatever. They're also color-coded. And so whatever is receiving the input has to be set up for that type of thermocouple input.
So we've got thermocouples, which are, again, we get back to a milliamp kind of signal. It's a different way of generating that, or how it's produced. What other sensors do you guys see out in kind of buildings?
Sensing bulbs, and use like a freon.
Okay, so we have a gas-based temperature sensor. We use them in freestats, bulb stats.
TXVs.
Yeah, so it's basically as the temperature goes up, the pressure goes up. So there's that equation on the bottom of the board there. PV equals nRT is the gas law. Pressure goes up, temperature goes up. They're directly proportional to each other. Okay, and so they use those, and that pressure can sometimes trigger a switch, but it also sometimes will operate a transmitter, right? And that transmitter could be voltage or it could be milliamp, depending on what the application is. Okay, so you got pressures, you got flows, whether it's airflow or water or some other liquid.
Humidity.
Humidity sensors, okay? And those sensors are typically, we're measuring the relative humidity in the space, and what then do they send us? Do we get a resistive, voltage, or a milliamp?
Humidity.
Does it tell us humidity?
No, just
It changes it into an electronic signal, right? And typically it's either a milliamp or a voltage. Okay. So all of the sensors that we work with basically come down to this voltage, current, or milliamp kind of a scenario. So we want to spend just a little bit of time talking about Ohm's law. Everybody like Ohm's law? Anybody remember Ohm's law?
Once you write it on the board, we will.
Well, I could do that. See if I can get the right one. Not that one.
We need to find somebody that can fix the temperature in that fridge.
Ohm's law.
Pressure sensor in there.
Now, I'm going to pass these out. Just take, I guess we can split it in half or whatever. We're going to do just a little bit of math. You guys are like, oh, dang it, I knew it. Why did I come to this? So this is kind of like a somewhat of a group exercise.
You've got two.
Oh, I've got two.
We're going to kind of work together a little bit on this, but what I want to do is first off just explain some of these terms. So Ohm's law, we have E stands for what?
Voltage.
That makes sense, right? E for voltage. Now, electrical potential is probably, but E is what represents volts in Ohm's law. I, amps or current, okay, so that represents our current. R, so that's the only one that really makes sense, right? We got that one. Okay, so these others are just kind of reworking the equation so that if I need to find current, or if I need to find resistance, I can do that. Okay, so what I'd like to do is have you, well, before we do that, let's talk about a few other things. If I have two resistors, and I want to see what their equivalent resistance is, and they're in series, I add them together. So if I take sensor 1, sensor 2, and I run a wire between them, and then I measure at the other ends, I should see sensor 1's resistance plus sensor 2's for a total resistance, right? Okay. If I do a parallel where I have, and the best example I think is the garden hose. I have one garden hose that has 10 GPM coming out of it, and I hook it up so that I have two garden hoses. Same flow, how much is coming out of each? 5. Because the pressure, the back pressure is the same, so the flow divides and goes equally. So parallel resistance is very similar. Is that if I have two identical resistances, the equivalent is half of whatever those two are. And you can prove that. If I have 1 over 10 and 1 over 10, that's 1, 2 over 10. Flip that over, 10 divided by 2 is 5. And so now I'm half of the 10 because they were in parallel. When we get complicated is when we have multiples resistances of different levels or different values in parallel. That's when this equation, you've got to use this, and it can get ugly, but we're just hopefully not going to get to that point in the class, okay? We'll just keep this basic. So those are some of the background there. What I'd like you to do is, and maybe we'll put one of these up here just to get this hooked back in. So on your first question there, it's giving you this little drawing where you've got a voltage source and you're coming over and you've got some sort of resistor or a load, right? That could be a light, it could be a solenoid, it could be a motor, whatever it is. In this case, it's saying it's a light. And we have resistance of 2200 ohms. We have a 110 volt source. And the question is if my current is going through that, what is it? Now, one thing I want to share with you is that as I move current through any single path, what is the current anywhere in that circuit? Does it change? What is my current here compared to here?
It's the same.
It's exactly the same, right? So current, as long as my circuit is established, never changes in that branch of the circuit. Okay. Now we don't have a bunch of other things tied to this, But in a simple circuit like this, whatever current starts will be the same that we see through the resistor. We'll see the same at the very end of this of the path. Okay? So how do I get how do I figure the current in this?
110 divided by 2200.
Right. So I have 110. So that's my volts, or E, divided by 2200, which is my resistance.
0.05.
And is that amps or milliamps? That's amps. How would I write it in milliamps? So to put it into milliamps, I take 0.05 divided by 1,000, which gives me 50 milliamps. Okay. So we're going to talk about 4 to 20 milliamp signals in a little bit, and I want you to understand that we're talking about really tiny current flows, right? We're not talking about big stuff. You got a blow dryer at home, somewhere in the house. Got daughters or a wife, right? Someone's got a blow dryer.
I have my own.
Okay. Scott.
You and me both.
Got two of them, right? Blow dryers about 1,600 watts, right? They pull a lot of amps. Okay, we're not going to go into the math, but they could pull 10 amps. You know, they can pull quite a bit of amps.
You can burn up a generator if you let her do it right.
Put enough of them on there, we'll do it. Okay. So anyway, where were we going with all of that?
Camping trip story.
Yeah. There's got to be something behind that one there, right? Just like, boom, it's gone.
Night.
Yeah. All right.
So
So
the blow dryer pulls a lot of.
the blow dryer pulls a lot of amps. Yeah. And we would figure that. So say you're 1,600 and you're 120 volts. So watts is equivalent to VA. Your blow dryer 1,600 VA or 1,600 watts. You divide 1,600 by 120, and you're what, 13 something? Yeah. So 13.3. Oops. Okay. So that's a lot of amps that it's pulling. All right. So in this case, we're pulling 50 milliamps, so a pretty small load to get this thing to work. Okay. I want you to do problem 2. Okay, anybody ready to tell us how we did this? Okay, Brett?
Times 40 times 0.1.
Okay. So before we do that, let's draw it just quickly. I mean, you're right on. So what am I going to have here? I've got a CD player, right?
Resistor.
DC power supply.
So here's my CD player. I'm not a 3D drawer. Let's do this. Here's my CD player, which is equivalent to how much?
40 ohms.
So 40 ohms. And it says that we have a current of 0.1 amps, which would be 100 milliamps, right? Okay. So 0.1 amp, and I have some sort of a power supply, whether it's AC or DC, doesn't say. Okay. So what's the equation then?
Ohms times amps.
So we're trying to find
E. E to give you your voltage.
E,
Equals I 4 volts.
I times R. So I'm 0.1 times 40.
4 volts.
Oops, not ohms, volts. Okay. So pretty straightforward, right? Okay. All right. What we're going to do now is do the problem 3 and 4. I'm going to go refresh our waters here, but you've got and some of you guys, if you want to come kind of buddy up with somebody here at the table, I don't know that we have enough to do everybody, but what I'd like you to do is using your meter, what we're going to do is we're going to hook these resistors in parallel and in series. So we have 2 cups up here with some water in it, and without really looking, Devin's going to measure this on his meter, and he's going to tell you what the resistance is, and
Take care.
that one's fine.
Sprinkler water tanks,
Well, it's gonna be about 32.
just saying.
70.
No, you can't. Look.
70?
Oh, you can tell him the ohms.
70.
Scott will be the spokesperson.
Cold water is 70 degrees.
You're not
Or
supposed to say
70.
cold though.
Say,
All right, so look up on your
You gotta
chart.
get,
the
you gotta
first
get up.
job-
Yeah, you got
On your chart, what is 70K?
It's like 32 degrees,
So around 32 degrees.
roughly.
So these are 20K.
20K what?
They're the far
20K
right, the
number
far
20K
right
on-
column,
yeah, you're
type
gonna be the
4s.
very far,
Okay.
far end.
And then what was the hot water?
What were you saying? What was the very first one?
70.
70.
Oh, okay. All right, so you're right around 32.
Okay.
And that's not because the ice is in that, sorry.
Well, that's what we would hope we'd be close. And then the hot water, we're measuring
47.
2.6.
Oh, you got hot water in there?
2.6K, so 2,600 ohms.
165. It's pretty hot.
160.
It was boiling a minute ago.
165.
6? Yeah.
So the hot
Yeah, you're
one's
165 or so.
Okay.
It's what?
So that's problem 4 that we're working on right now.
I'd say yeah, it's 165. I put my finger.
It feels 165.
It did hurt. It's not
It's
comfortable.
all red.
It's not
So
comfortable.
what was the cold one turned out to be?
23 degrees,
It was 70.
70K.
Now, what I want to show you really quick is problems 5 and 6 are advanced problems. We're not going to do them in this class, but I'm just going to give you a little insight. I would love to see you try them and then stop by and visit with me about it sometime. We're not going to really spend the time. I'll tell you a little bit about it, but it's using kind of the principles that we've talked about. Here on campus, we do something very similar to the last thing that we just did with the 4 resistors. We take and we do a resistor, or a thermistor, I should say, and we'll put 4 of them in some sort of an air handler for mixed air or whatever. And if we hook them up, like we did in the lab,
Series parallel.
they look just like they're one sensor, right? You remember how, because you've got these 2 together double, those are doubled, so if we're doing our lab, we got 20, 20, so I'm 40, but then 2 40s in parallel, half it back to 20, right?
So what is the advantage of doing it that way
Averaging.
over just one?
Well, if I have a big coil, I might get cold or warm spots, and it allows me to get different areas and to average electronically what that temperature is. Now, we can do more than just 4 sensors, but the way that this works, let me back this up a little bit. If I'm going to do more, I have to do something like this. If I do 4 and I want to really get a lot of good average, I have to do 4 rungs of 4 sensors. If I want to do 5 rungs, I have to have 5 sensors in each rung, right?
You can't be off.
It has to be a square, essentially.
Yeah, and this
That-
is kind of what we're doing with our averaging thermostats. What we're doing in a
It's
sense.
done differently. It's actually done. It's done programmatically, not electronically.
Okay.
So it's
They're
different.
all coming back to the.
They come back as individual sensors, and then we just average them.
Okay.
So I can do 2, I can do 3, I can do 4, and it doesn't matter.
Okay.
I could
You're
do
doing it
6.
But if you're
But-
doing them like this.
But if I'm doing them with physical sensors, I have to have the same number paralleled as are in series. So I have 4, I have 1, 2, 3, 4 in series. I have 1, 2, 3, 4 rungs of those. So these are squares, right?
Right.
If I had 2 to begin with, so it gave me 4, right? 2 squared, 3 squared is 9, 4 squared is 16. Honeywell makes a sensor that has 25. Why did they pick 25? Because of this principle. They do 5 across, 5 sets of those 5 in parallel, and it electronically averages during that whole array. Okay. Honeywell take and they put them in a long string, but they're wired like this. Okay. I'm glad we have background noise.
White noise.
White noise.
White noise.
Yeah.
Oh, really?
Okay. So this question that we have on number 5, so it talks about we have an air handler, and I have 15 sensors in a box. Okay, I may use 15, I may not. But remember what we just talked about, parallel series have to be the same. Okay? And I'm going to put those somewhere on this coil. So if I do that, it's saying, and if my temperature is 60 degrees, so what's my resistance at 77?
10 or 20.
I'm at 20. But if I'm at 60 degrees, what's my temperature, or I mean, what's my resistance?
3144.
Okay? It changes, right? It's not 20 anymore. Okay? So as you put that on as you work out the math, it's not as easy, is it? 31, like 1 over 31, 1 over 31, 1 over 31 for the, the parallel series thing, it kind of becomes a little bit of a mess. But it's doable. So if you want to have a little challenge, you can play with 5. 6 says is one step harder. Say one of the sensors that you use fails, and I'll tell you right now, you're going to use 9 sensors. I'll give you that hint. Say one of the 9 fails. How does that affect the overall resistance that you see at the controller? Okay, so these are things that happen. I've had this with one of those Honeywells. We had one of the sensors fail, and our resistance of the whole averaging sensor changed. Is that sensor throwaway now? You can calibrate it, because now all of a sudden you skewed everything, and it will kind of track but offset. So you just have to know how to do that. But play with that if you want. And if you think you come up with an answer, come see me, and we'll see how you did. Okay. One thing I want to talk about that we haven't yet, and we're getting closer to time here, is our 4 to 20 milliamp signal. So we talked about the reason we use our thermistors is because of they're inexpensive. Okay, there's a fairly simple installation, right? I just throw it out at the end of a pair of wires and I'm good. The one thing that we didn't talk about with thermistors is they are susceptible to noise, right? Because you essentially got a long antenna. I got this big wire, goes out and back. It's just like a big antenna. So if there's a lot of electrical noise in like a big, mechanical room, it's got a lot of VFDs or other things, switching going on of some sort, that sensor can then pick up those electrical magnetic impulses and signals that are in there, and it can throw off our sensor. So to overcome that, we use this 4 to 20 milliamp signal. What did we say that an amp or the current in a circuit is? It's the same all the way through the circuit, right? So if I've got an antenna that's picking up voltage and doing weird things, is that going to affect the milliamp signal? Sorry? It shouldn't, right? Okay, because my milliamp should be the same, and it's all based on my transmitter. This transmitter is built so that it just puts out between 4 and 20 milliamps. Now, why did we pick 4 and 20 milliamps? Why would we, or why did whoever picked that originally do that? say they had picked 4 to 20 amps.
It's not safe.
Okay,
But that's
wouldn't
a
be
lot.
safe. What would our wire size do?
It'd be a lot
Wire
bigger.
sizing.
Right, we talked about 12 gauge for a 20 amp circuit, right?
Yeah.
I don't think we want to run 12 gauge wires out to every one of our sensors, right?
Keeps
So
the cost down.
what if they would have done 0.4 milliamps?
Harder to read.
Yeah, it gets so small you can't read it. As it is, it's tough unless we have the right equipment, right? Okay, so 4 to 20 milliamp, at some point somebody said, that works pretty good. And if I pick the right resistor here, I get a really kind of cool thing that happens. If I put 500 ohms right here at 4 milliamps, which is 0.004 amps, I multiply current times my resistance, I get my voltage drop of 2 volts. If I do 20 milliamps through a 500 ohm resistor, I get a voltage drop of 10 volts. Now those are numbers we use a lot, right? 0 to 10 volts is right in kind of our area of working with stuff. It's a safe voltage, it's DC, it doesn't take a lot of componentry to build a transmitter or a power supply to generate that. And so my power supplies don't have to be huge. Okay? I've got a signal, 2 to 10 volts. I can read that really easy with a meter. You know, that's a pretty readable value. When I get into millivolts or thousands of volts, I don't want to be near thousands of volts, right? We want to stay well away from that. But this is a good place. Why do I use 4 instead of going all the way to 0? What benefit does that give us, or does it?
We take some to get something to
Yeah,
start
you gotta have
working.
something going.
Okay, so if I'm troubleshooting and I see 4 milliamps, what does that at least tell me?
Yeah, you got a signal there.
Something's working.
Yeah,
I may
you
not
got a
have
zero,
I
nothing.
may not have the sensor working right, but I know I've got power, I've got a transmitter that's doing something right. So it kind of gives me a baseline to start my troubleshooting off of, so that I'm not totally out in left field and not sure what's going on. Okay. What are some of the challenges that we run into with a 4 to 20 milliamp circuit? Are they as easy to measure as a straight up 0 to 10 volts kind of signal or a resistive circuit? Can I just pull wires off and put a meter on, measure my resistance like we did before? No. If I pull off the terminals, what happens to the signal? I get 0, right? Because my transmitter doesn't have power anymore. So this takes a little bit more kind of finessing to get to a point where we can read a value that works. Some of the things that I can do, if this resistor here is in a place that I can put a meter on it, will I read a voltage drop there?
Through the resistor?
Yeah,
You can read voltage drop through.
I will. I absolutely will. Okay, this right here, because I have current flowing through a resistor, Ohm's law tells me I will have a voltage drop across that. The current is constant, there will be a voltage drop. So I can use regular volt setting on my voltmeter, put it on there, and I should read it. Now, if this is 500 ohms, I'll get between 2 and 10 volts. We can also do a 250 ohm. So if it's half the ohms, what should my current be? Sorry, what should my voltage be?
1 to 1.5.
It should be half, right? So if I was 2 to 10, I'm now what? 1 to 5. So those are another kind of signals that you'll see out there is a 1 to 5. Kind of depends on what I have here. Is my controller looking for 1 to 5 or 0 to 5 or 0 to 10? It just depends on what resistor they'll use here. If I put a 500 ohm resistor there and I have 10 volts drop, okay, I need some power here to drive or to run my transmitter, and maybe that's 8 or 10 volts. We'll say 10 just for the making math easy. So I have 10 volts there and 10 volts here. How big does my power supply need to be?
20 VA.
So at least 20 volts,
Wait.
right? So it needs to be
That's
at
right.
least a 20 volt, and that's if I don't have any line loss because of this. Now, milliamps, how far can we run a milliamp signal? Fernando?
I don't know the limitations, but we go pretty far.
Can we go further with a milliamp signal than a regular like thermistor resistive thing?
I don't know.
You could do both long, but you'll be more accurate with a 4 to 20 milliamp on longer distances. Because remember, if we're doing resistive, especially if it's an RTD, the longer I go, the more error I introduce, right?
Yeah.
So if an RTD is 100 ohms, and I got 3 ohms of resistance, that's a 3% error just in the total range. If we look at the, like the smaller amount, it may even be more. So this needs to have at least some capacity to also have voltage, because that's like a big resistor, right? It's just a really tiny resistor stretched out over a long distance. So I may have a little bit, like maybe a 1 volt drop on each one of those legs of that wire. So if I'm 10, 1, 1, and 10, I need at least 22. So what do we usually put in for our power supplies? Probably a 24. That's very typical, 24 volts DC, okay? And that'll take care of powering up our transmitter. Transmitters sometimes don't take 10 volts. They typically will be at least 5. Much of the digital world is based on a 5 volt signal. A lot of the Staples Smart 2 cards, all of the componentry is based on a 0 to 5 volts. Their comm line is 0 to 5 up and down. Their inputs are 5 volts, 0 to 5 volt inputs. And if we have milliamp, resistive, or voltage, it all gets converted into that range. Okay, so we need 5 volts for this to run, and usually a little bit more because there's some losses due to heat and things like that. So 10, 6 or 7, 7, and maybe 1 or 2. So 20 volt power supply could get us by, except what would happen if I have 20 volts and I pull 10 here and 10 here, and then I got 2 on this wire? What's going to happen to my signal?
It drops out on the voltage to run it.
Okay, so does it drop out on the whole range?
No, on some of the,
Where does it drop out for?
your 210s would drop down.
Okay, one of them would. This one's going to have 10 volts to just run, right? But here's what happens. Say I need 22 volts to run this. That's only when I'm at 20 milliamps, right? If, say for instance, I'm at 4 milliamps, I put 4 down here, I've only got 2 volts drop there, 2 here, so I'm 4 plus 10, I'm only 14 volts. 20 volt power supply is fine there, right? But as I start to ramp up and I move from 4 to 20 milliamps, I start putting more and more of a load on there. And as I start to push more current, the voltage drop on this goes up. As I hit that point where I hit my 20 volt supply, I start browning out my power supply, and it no longer has the ability to push any more down the wire. And so you end up kind of going as a straight line up the curve until you hit your max voltage, and then it plateaus. Okay. So if you're troubleshooting this, can you just troubleshoot the 4 milliamp portion of the signal? No, you got to do the top end. The top end's probably more critical to make sure, but usually, like if you're going to run it through the range of low to high, you want to make sure to get the top end and then make sure it ramps between the two. Okay. What else? Any
So
other?
what would we see? You said browning out. What are some symptoms of that?
Okay, so say for instance, your sensor, whatever it is, say it's a pressure sensor, and it's supposed to do pressure from, say, 0 to 5 inches, say 0 to 2, so we don't blow anything up. And you know you're over 2 inches on this particular sensor. You've got a gauge on the side of the magnet helix or something that says you're off the above 2. So you're like, I should be 20 milliamps. And I go and I put my meter, say I can get to that resistor, and I put my meter across there, and I'm reading 16 or 17 volts. You're like, well, that doesn't make sense. Why am I reading that? Okay, because I should be all the way to 20 milliamps or 10 volts. Okay, so the way that you do that then is you back it down and you keep your meter here. And what will happen is your meter will stay 16 or 17, whatever it was, it'll stay 17 volts. You keep backing down the sensor, and then all of a sudden, it no longer will say 17, it'll start to come down. Okay, and that's one way to troubleshoot it. Now, we don't always have a way to do that, but if you have a VFD, that's doable. Say the VFD is all the way at 100% and you're doing everything you can and you're still showing 17 volts, then you slowly bring the speed down to the VFD and you'll eventually see that thing drop off of it wherever it was locked on. And so then okay, I may be browning out on that or not have enough voltage on my power supply. So the other way that we can overdo a power supply is if I have a couple of these in series. There is a way that you can do, if we have a 250 ohm resistor here, then I'm 1 to 5 volts, I could put a second one in series and I'll have 5 volt drop here and a 5 volt drop on the next one, and this power supply could handle 2 things. So what I've done before, I've seen done, is one source drives 2 VFDs, and the VFDs are in series. So my wire comes in one, goes to the next, and then comes back to the controller. And both VFDs will track. But we have we have to make sure that this resistance doesn't exceed what the power supply can handle. A lot of times transmitters will have kind of a rating on there, can drive 750 ohms or less, 600 ohms or less. And so you just have to make sure that whatever, like if I want to put a VFD here and then a meter, like a digital meter like this next to it, you could do both, but the combined resistances have to be 750 or 600, whatever it's rated for. Why 750? A 500 ohm resistor and a 250 ohm resistor in series, 750. And so you could do 2 devices, so long they're both 500. It's too much; it'll brown it out on those on the upper end. So, how do we measure this? Real quick, because we're getting close on time. How do we measure a milliamp signal or troubleshoot it?
2 ways.
Okay, give us one.
Measure the voltage drop across that resistor.
Okay, so we mentioned that before, and you can do a voltage drop there. If I can't do that, what are my options? There's another one.
Clamp.
So an amp clamp, if you have a
You have to
milliamp
multiply
clamp.
You have to maybe.
So there's a way to wrap it. When you're dealing with milliamps, you'd have to wrap it 100 times.
Yeah.
It would be a lot. So that, because 100 times would get us to 0.4 of a volt or 2 volts, right? Because we're 2 to 10. Sorry, we're doing milliamps, so it would be 0.4 amps to 2 amps if you wrapped it 100 times. But you're right, you could do that. You just have to have a really thin wire and patience.
Yeah.
Okay.
And count.
So-
Don't lose count.
The way that we sometimes have to do this, to measure this, is to open the circuit and put our meter in series. So I would, disconnect somewhere, but I have to keep the circuit running. So I'd put my meter. So here's my milliamp circuit. Kind of the way this was done before. This is some sort of a meter. And then what I would do is I would break my circuit. That's an arrow. And my meter, I'm going to take one lead there, one lead there. What do I have to put the setting on? has to be amps, or if you have milliamps,
DC metal.
DC. You may not have a meter that does the milliamps. If you put amps on, is it going to read anything? It'll be too small, right? You're an order of 1,000 different. And so, as long as I keep this in series, what?
The leads, it's critical that you change your leads.
Yeah, the leads on some of these, and most meters, you'd have 3 connections, right? There's a voltage connection, and then you move it over to the amp connection. What would be your guess if I was 500 ohms up here? How is my meter reading the current that's flowing through this? What is the meter doing inside of itself when I hook this up?
It's a resistance also.
It's got a resistance, right? And then it's going to measure the voltage across that resistance. What size of resistance do you think the meter is going to put in here?
Pretty small.
It's going to be tiny, right? 500 ohms, I don't want to change the circuit at all, so I'm going to stick a tiny, now if this is a current source, I could put 250 there, it won't change the current. But if I'm not got a current source, this has got to be like 1 ohm or half ohm, quarter ohm, something like that, really tiny resistance, so I don't manipulate the circuit as I read it. And so what happens if I put a teeny tiny resistor in there with a big voltage? And
Yeah, it blows it.
well,
Fuse.
you can get a lot of current flowing, right? So that's why you got to be careful on how you hook this up. You can't just take a milliamp setting on an amp circuit, because it will pop the fuse. It doesn't take much.